So, in our final video on the radioactivity subtopic, let's get into our application for this subtopic, which is PET scanning. Now, I know some of you have looked at this as your issue investigation, so hopefully you are already experts on this, and you can tell me all the things I do wrong. Okay, it's raining quite heavily here, so I hope that's not coming through too much on the video. So, PET is an acronym for Positron Emission Tomography. So, I guess the most important term for us is the IAE concept of a positron. And hopefully that you're aware that a positron is released during beta plus decay. So the most common isotope used in PET scanning is fluorine 18, which is this one down here. And the fluorine 18 is actually incorporated into glucose. Our body uses glucose wherever it needs energy. One thing in our body that particularly needs lots of energy is tumours. Tumours need lots of energies to grow. So if you've got some sort of tumour, that will tend to use lots of glucose. So if you add this glucose that's labelled with fluorine 18, it will accumulate in that tumour and therefore release radiation where it accumulates, and that is going to be the start of the process for detecting your tumour. So, I think we've covered the fact that some radioisotopes used in PET can become concentrated in certain body tissues. Then, describe how beta plus decay of a radioisotope can result in the production of photons through positron electron annihilation. So, we already sort of talked about this, but our fluorine 18 undergoes beta plus decay. So we get a proton is converted to a neutron. So we lose, if you like, a proton. The proton gets converted to a neutron. The number of nucleons stays the same. So it becomes oxygen. And we get our beta plus particle released. And we obviously also get our neutrino and our gamma ray photon. Talked about the reasons for those before. Now, this positron that is formed will very quickly collide with an electron. So the positron basically collides with an electron that surrounds one of the atoms. So this positron comes from the nucleus. The electrons are just all the electrons that surround all atoms. And when this happens, the two of those annihilate and produce two gamma ray photons. So they collide. The reason we get two photons is momentum must be conserved. So, for momentum to be conserved, we need two things going in opposite directions so their momentums cancel out. So, this is basically how we use an isotope that undergoes beta plus decay to set up positron electron annihilation and the production of two high energy photons travelling in opposite directions to satisfy the law of conservation of momentum. Just basically covered that point. Now, we can actually work out how much energy these photons have using E equals mc squared. And we know, in this case, the mass of an electron equals the mass of a positron or a beta plus particle, which is equal to 9.11 times 10 to the minus 31 kilograms. we have 2 of those, so basically we times that by 2. We plug that back into the formula, and I can't be stuffed working it out, but from memory, and I'm sure Hannah's going to tell me if I get this wrong, you work out that there is about 512 kilo electron volts of energy in each photon. So both photons have that amount of energy heading in opposite directions. I want you to try and calculate that just to see if you can prove if I've made a mistake or not. Now, how is this useful? Well, when you go to have a PET scan, you're placed on, if you like, a bed. You're injected with the fluorine-18 containing glucose. I think you have to let it soak through your system for half an hour or whatever. And then you're placed into this ring detector. Now what happens is the glucose accumulates where the tumours are, and then you get this positron-electron annihilation, because these positrons that are produced travel, less than a millimetre probably before they hit an electron and are annihilated. And when this happens, we get 2 photons released, one going one way, one going the other. Now, this ring detector can very, very accurately measure the time that these pairs of photons strike, and it can then calculate from the difference in time, basically the difference in distance that each of these travelled, and it can therefore isolate the exact point that that emission must have occurred. So if in this case, if T1 equaled T2, that would mean that the 2 photons had travelled the same distance, and the photon must have come from a point midway. In this case, if the photon was, go to blue, if the photon was here, then T1 would be less, because it would travel less distance to there than T2, and that time difference between that 2 would tell you how far, if you like, you were from that midpoint. So, this happens over, the scan is done over, I'm not sure, don't remember exactly how long the scan's done over, but it's done over an extended time period. You get lots of these positron-electron emissions occurring, and it allows you to build up a picture of that area where glucose is being used at a much faster rate, which is quite likely to be a tumour of some description. So you build up that internal 3D image of the body. So hopefully that covers how we describe how a ring of photons allows the location of a tracer isotope in a human body to be determined. Now, a similar process can also be used to trace blood flow, but in this case they use oxygen 15, and they use that within water. Add that to water, and obviously our blood transports a lot of water, and this is used to help trace blood flow through certain parts of the body, but similar process to what we've just talked about here for using fluorine-18 to isolate a area where glucose is being concentrated. I just saw this here, I must admit, normally we talk about PET scanning for tumours. You can also look at how the heart's working by looking at how the heart's using glucose. I picked really that one was there. We tend to normally often talk about tumours. Final point, explain why PET facilities need to be located near particle accelerators. Well, in that previous question, we just saw the half-life of fluorine-18 is, 110 minutes. So obviously, if we don't do this PET scan close to where the cyclotron that makes the fluorine-18 is, then it's all going to decay before it gets to the PET facility. And the reason we want to use fluorine-18 and maybe not some other isotope that has a longer life is one of the ways that we can minimise the risk of damage from ionising radiation is to minimise time of exposure. So it is in our health interest to use something that has a short half-life, and then obviously if we're using something that has a short half-life, we need to use it close to where it's produced, otherwise it will all decay before it reaches us. That's it.